各位大家好 Hi everyone, welcome back. Today I will review a paper titled Deep Learning Segmentation Method for the Optical Coherence Tomography Angiography or OCTA in the ophthalmology, and this paper is quite interesting. So we knew that the doctor can use the imaging technique named OCTA to see the blood flow or the blood vessel inside our retina in our eye in a non-invasive procedures. OCTA can create a detailed scans, also segmentation layer by layer of our eye, but analyzing this one will be time consuming and sometimes can vary between the doctors. So here's the deal of the idea, using the deep learning to enhance the imaging technique, especially can also automatically segment this eye scan. And in this case, we will teach AI or our model to identify the blood vessel, tissue layers, and also other area in our eye with faster and more accurate than traditional methods. For ophthalmologists, this will be helpful for the quicker diagnosis and also the better detection of the disease like the diabetic retinopathy or the glaucoma. So the impact of OCTA and also deep learning can help for the future medical diagnosis. And without further ado, let's talk about this paper and review it together. So here first I will talk about the outline in this presentation. First I will talk about introduction, the motivation and the purpose behind this research and its impact for the future medical health diagnosis. And then in the insights, I will talk about the popular imaging technologies, especially in the OCT, and also the overview of the optical disc and the macula. In methods, I will talk about how OCT works, especially in the OCTA system, and also the framework from this deep learning model, that is the coarse and fine attention based network or CFA-net. And also in the results, I will of course talk about the results of the imaging by this framework and also the visualization of the heat map with this kind of framework. Then in the conclusion, I will talk the future and also the summary of this research. Let's begin from the introduction part. So, optical segmentation is one of the most important part in the eye imaging technique for the ophthalmologists, because to diagnose the retinal disease, usually the ophthalmologist will see the imaging from the optical disc and the macula. So this kind of imaging technique will be very important for the doctor to determine the correct treatment for the patients. And one of the way to imaging this eye is using OCTA, because by OCTA it can directly imaging the optical disc, retinal nerve fiber, macula, and another layer inside our eye with non-invasive procedure. And then convolution neural network and also the RNN can help to understand this vision imaging and also the language. But the problem is the boundary blurring and the low contrast in image segmentation. So as we can see in this feature 1, so even though we can see the correct and quite clear about the inside our eye, but sometimes like the blood vessel and in here the optical disc, sometimes it's not quite imaging or quite segmented very clearly. But deep learning can help further improving this imaging from OCT to have more better contrast and also the better segmentation, the better and the improving of the clarity of the image itself. Here is OCT or optical coherence tomography. OCT is usually used as the non-invasive imaging, especially in the retinal case. Also, maybe the minimal invasive imaging for in vivo, like for the brain surgical process. And the application of OCT can be used as the clinical diagnosis, disease monitoring and assessment, on of course the biomarkers. And in this paper, we will talk more about the eye segmentation. And the idea of OCT is quite simple. It's using the interferometer system with the low coherence light and to see the delay of the intensity of the constructive or destructive interference pattern. So purpose of this research paper is to construct a new optical disc and macula in fundus image with the optical coherence tomography OCTA dataset. Then is also use the proposed novel framework named coarse and fine attention based network or CFA-net. Then we can use the coarse and fine features from the eye segmentation of the optical disc and macula to have further imaging of the OCT, and design this coarse grain feature extraction module then can help the extraction of the coarse features from the original image, and finally propose the fine grain features to enhance and also extracting the fine feature in the original image. Then let's talk about the insight from this paper. So in the medical imaging technology, there's several popular methods, that is the X-ray, the NMR, ultrasound, MRI, and of course the OCT. And based on this table 1, we can see its resolution for its imaging technique, and also the damage or the invasive or not for this kind of technique, the speed, and also the specific task of this imaging technique, and finally of course the cost. So among all this imaging technique, we can see that OCT has quite better resolution, even not as too deep as the other imaging technique, but this damage is none, so it doesn't have affecting of our tissue or our organs, and the speed is quite fast, and the cost is very low compared to other technique. And OCT utilize concept of interferometer to generate scanning of the cross-section of our retina, and the resolution still can reach around 15 micrometer with this kind of technique. The principle of OCT based on the coherence and the tomography. Coherence in the optical system means the phase relationship between different points in a wave. In OCT, it uses the Michelson interferometer system with the low temporal coherence. So in this case, we need to maintain the phase relation between its reference arm and the sample arm for recombination and the interference. And the short coherence length can determine the depth resolution of the OCT image. And the tomography itself is actually the cross-section image or slice of the 3D object from the multiple measurements in our organ or cell tissue. First, we have a scan, a single scanning that provides a depth profile or the 1D line reflection. Then the multiple of A scans can be compiled to form a B scan or two-dimension cross-sectional image. Like this feature, we can see the eye layer, like the retinal thickness and the choroidal thickness, and so on. And by stacking these numerous of B scans, we also can make a 3D volumetric image that named as the C scan. OCT itself, in general, there is a two types, the spectral domain OCT and the swept source OCT. These two are the Fourier domain OCT. So the basic idea is using the extracting the signal from the OCT system and using the Fourier transform to help to image this kind of signal. And in this paper is focused on the swept source OCT. So swept source OCT is using the single photodiode detector and also the balance detector to balancing between the reference and the sample arm. And it has higher imaging depth. It can also have a tunable laser that swept as a light source. So this is one of the main characteristic of the SSOCT. But sometimes it's still constrained to low resolution imaging. And in this case, that's why we use machine learning or to help the resolution can be better and have more improvement. For the optical disc and macula segmentation, in this paper, they use the neural network, and that also usually used as the multiple medical image segmentation, such as CNN, and also the FCN, the full convolution network, and the UNet. UNet is one of the most popular framework in the medical imaging technique. So it's used the symmetric U-shape architecture, and the main idea is using the skip connection, so it can fuse between the low level and the high level features. And then FNet also combines the previous epoch's mesh and also unified with this current epoch's feature map during the training. By this way, it can improve the efficiency of the multitasking model and exploit the association between the optical disc and macula simultaneously. So, as you can see in this picture, is the UNet framework for the biomedical imaging segmentation. We can use some skip connection to directly to have more efficiency for the model to learn and train with the medical image. Okay, now we move to the third chapter. So first in this chapter, they construct a new dataset that named optical disc and macula in fundus image, or ODMI. So this model dataset can be used as the segmentation for the machine learning to learn. So they describe some information on the ODMI dataset with the existing of the diabetic retinopathy dataset. So as is seen in this table 2, it has the list of information of the common fundus database. Mostly existing external datasets have image level annotation, and the several DR datasets or diabetic retinopathy datasets also have a pixel level annotation for the lesions. In this dataset, they use the 50 image, and the main test is already mentioned, the segmentation, and the image size is 288 times 288, and the modality is gray or the black white as the modality, and data taken is during the 2023 year. And compared to the other datasets, it's maybe a little bit smaller, but this still can be used for the simple segmentation for the machine learning to learn. Then how does this image can be formed? So it's basically from the whole imaging process in the OCT. So first, light incident will pass through the sample tissue during the sample arm, and in this tissue they will have some absorption and scattering. After the light incident from the backscatter recombined with the reference arm, the electric signal from the detector will be inputted into the computer, and this interference signal then is using by FFT. It changes to be the interference signal of the A scan. So with the Fourier transform, we can transform this interference signal to be as the depth scan of the A scan of the imaging tissue. And as in this picture, we can see the interference signal is transformed to the depth scan, and the error signal usually rejected here. And then by the A scan, we got some multiple A scan can be formed as the B scan. This B scan is the cross section of the tissue, as we already mentioned before, and this repeated B scan can also record the contrast of the blood following blood cells. So that's why we can also see the macula and the optical disc later by this B scan. Here is the system diagram of the SSOCT that used in this paper, as in the feature 3 and the feature 4. So we can see the balance detector, the interferometer setup, the reference arm, and also the sample arm of the tissue. So they use the high-speed scanning laser, and the penetration to the detect per fundus around 1.5 micrometer, and the scan rate is around 100 kilohertz with the robust laser with the longitudinal resolution is 9.4 micrometer, and the maximum imaging depth it can until 9.6 millimeter. B-scan also can be viewed as the number of N-phase repeating scan as the depth, as in the feature 4. So we can see the multiple A scan. By the N-phase we can see the B scan, and this N-phase will be keeping the axial coordinates and allow the collection of the constant depth imaging in the real time. Okay, next I will talk about ODMI dataset. As already mentioned before, this ODMI dataset consists of the retinal image database for the segmentation in the human optical disc and the macular with the OCTA. So we already have the 50 normal subjects with optical disc and the macular image, and also the 50 of the ground truths in the total. So the ground truth also already cross-checked with the ophthalmologist, and the resolution of each image is the 288 times 288 pixels. So these ground truths are labeled manually by the ophthalmologist. As you can see, this white circle here is the optical disc and the macula. So we can use this as the base for our training model. Now we will talk about the framework or the architecture of this deep learning model. So in a given retinal OCTA image with an optical disc and a macular, the proposed network will output the segmented image of this optical disc and the macular. And in this picture we can see the overall framework that consists of the four main components: input, backbone, two modules, and the segmentation output. To segment the optical disc and the macula fundus of image with OCTA, this framework named as the coarse and fine attention-based network or CFA-net, including the two key modules, coarse-grained feature extraction module and the fine-grained feature extraction module. And this CFA-net can integrate between the coarse and the fine features from the optical disc and the macula, then segmented at the output and in the end-to-end manner. In this framework, we also utilize the classical network as a backbone, such as CNET or context-to encoder, and the UNET to extract the global features. UNET itself has some weakness in the consecutive pooling and the strided convolutional operation that somehow it can lost some spatial information, and the CNET can help to capture more high level information and to preserve the spatial information for 2D medical image segmentation. All the extracted features will be fed into the refinement module to obtain the refined map. Then we'll fuse with the global features and also the refinement features. This segmentation result of the optical disc and the macula that obtained by the CFNet. Then we also use a skip connection in the CNET to fuse the features with the same spatial resolution at a single scale. Then for the main framework, we will use the CFNet to effectively learn about feature information between the coarse-grained features and the fine-grained features. So we will divide it as the coarse-grained features and the fine-grained features for this OCTA image. And these features will help the model to learn from the fundus of different scale, that step by step from low to high level. Each module will contain about 4x4 convolution kernel, batch normalization, and the nonlinear function or LILU, and also the residual module. This 4x4 convolution kernel will allow the neural network to obtain the effective features. Then batch normalization will convert this data distribution of each layer into a normal distribution. Then can make the network will coverage it faster. ReLU is a parameter-free nonlinear activation function, and it allows the network to reduce the gradient disappearance. And the residual blocks can mitigate the gradient explosion of the neural network. This feature 7 is show the details of the CGF and the FGF attention modules. First, we will talk about the coarse-grained feature extraction module. So this proposed CGF module, as in the top side of this feature, will focus on the capturing the global features from the maps and can effectively learn from the features of the optical disc and the macula by increasing the receptive field. Then the backbone output feature maps with the formula with C times H times W. This will become the 4 times C times H times W with the 2 upsampling operation. This method can increase the receptive field of the optical disc and the macula and can identify the area more accurately. And finally, we can rewrote this formula as this AM, phi, and convolution, and also ReLU and the batch normalization here. Now for the second module, the FGF, fine-grained feature extraction module, in the bottom side of the feature 7, will show the purpose of this model, and it's focused on the capturing detailed features from the fundus. With the skip connection in the ResNet, the detailed features of the region are preserved, and the edge of part of region is still enhanced. The bottom branch will use the ResNet network to generate the features, and the formula will follow as this formula T. 2. Then based on these two equations, we can combine it as the new formula in the formula 3 that can show the relationship between the CGF and the FGF. And this also denotes the multiplication that can enhance feature computed by the CGF and the FGF. The final formula, as mentioned in the formula 4, with the W here as the pointwise attention weight of the same shape of the input, and the value range from the 0 to 1. This plus will denote the addition of elements. The range of value indicates the future importance of its spatial point in its input of a feature map. By using this operation, we can target the regions more accurately, while identified non-target regions will be suppressed. Now we move to the result and discussion chapter. First, we will talk about the data augmentation and data partition. So in the data augmentation, we know that we have access of 50 original images and the 50 ground truths in our ODMI dataset. Then we will expand these samples by using 5 types of augmentation operation, such as adjust the brightness, saturation, contrast, horizontal flip, and the rotation operation with the original photos. After we add the data augmentation, we will perform the necessary pre-processing on each dataset, including the normalization. And to ensure the reliability and the repeatability of the ODMI dataset, we use partition on the dataset into training set and the testing set randomly. This can improve the generalization of the model. And all this experiment will conducted by using the 5-fold cross-validation. 40 original samples are selected as the training set. With the data augmentation, there are 240 augmented samples for training in total. 10 original sample pairs are selected as the test set. Then we can report the 5 metrics of the test set performance as the base score evaluation matrix. After some calculation, now we can evaluate matrix result and the comparison with the other model, as in the table 3 here. So in this table 3, we can see that all the models, also including the 5 parameters: sensitivity, specificity, size coefficient, accuracy, and the F1 score. And the CFA-net modules can achieve the highest rate of the segmentation on the ODMI dataset. Specifically, it can reach around 98.99%, 98.47%, and so on. Now in this feature 8, we can see the visualization of the optical disc and the macular segmentation and the ground truth. The ground truth is the GT here, and although it's not very obvious difference of the CFA model and the other model, but we can still see the CFA model can show more clarity rather than the other model, and much more closer to the ground truth from the ophthalmologist assessment. And now in the beside here, there is a feature 9, a heat map visualization. This will represent a relative intensity of future maps. Pixels in the blue color is denote the cool, while those in red mean hot. So the experimental is using to observe the attention maps, and these heat maps of the CFA net can have a better understand in the effects of attention. We use several OCTA images from the ODMI dataset. Then this model with addition of the CFA net can generate better results than the model without the CFA net framework. For the model without the CFA net framework, some irrelevant regions may still be identified. Specifically, for the segmentation of some irrelevant regions in the 5th row of the figure 9 here. The overall effect somehow also worse than those in the 6th row. It also can be seen that the attention model of the CFA net and this one can suppress the unwanted regions. More accurate interpretation of segmentation are really useful for the clinical treatment from the ophthalmologist. Finally, in the conclusion, this paper really introduced some new ODMI dataset. This image in the ODMI dataset will have a rich fundus details and the contextual information. This paper also proposed a new framework named CFNet that integrates the CGF, coarse grain features, and also the FGF, fine grain features, to retain more spatial details for the optical disc and the macular segmentation. And for the future works, this researcher will collect more OCTA fundus imaging and further improving the network structure to have more accurate and better segmentation for the optical disc and the macula. This is also the reference of this presentation paper. Thank you for your attention and have a nice day.